Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center for making this series of webinars possible. Our topic today is rainflow cycle counting for random vibration fatigue analysis. And this is really a very important topic because rainflow cycle counting is a very versatile tool which can be used for many different applications. As we often mention in this course, structures and components must be designed and tested to withstand vibration environments. And these components may fail due to yielding, ultimate limit, buckling, loss of sway space, etc. And fatigue is often the leading failure mode of interest for vibration environments, especially for random vibration. And previously we've discussed Dave Steinberg's quote, but let's review it. The most obvious characteristic of random vibration is that it is non-periodic. A knowledge of the past history of random motion is adequate to predict the probability of occurrences of various acceleration and displacement magnitudes, but is not sufficient to predict the precise magnitude in a specific instance. So when we're dealing with random vibration, it all becomes a matter of probability and statistics, and that will certainly carry over into our rainflow fatigue analysis. Now, having said that, the same rainflow fatigue methodology can also be used for sine vibration or even shock or any type of dynamic environment whatsoever. And here's just a little brief information on fatigue cracks here. And we're going to start off at the microscopic level. So a ductile material subjected to fatigue loading, or sometimes we say variable amplitude loading, experiences basic structural changes. And the changes occur in the following order. First, there's a crack initiation. So a microscopic crack begins to form within the material. Then there's localized crack growth. So local extrusions and intrusions occur at the surface of the part because plastic deformations are not completely reversible. Then crack growth on planes of high tensile stress. The crack propagates across the section at those points of greatest tensile stress. And then there's ultimate ductile failure. The sample ruptures by ductile failure when the crack reduces the effective cross-section to a size that cannot sustain the applied loads. So that's fatigue cracking for ductile materials. Now, just as a caveat here, so here's a picture of a baseball stadium. And the vibration fatigue calculations that we will perform are really just going to be ballpark calculations. And that's true no matter what our fatigue methodology is going to be. And that comes about primarily because there's uncertainties in the SN curves. Now, the SN curves relate stress along the y-axis to the number of allowable cycles along the x-axis. But these curves, it's very complicated to get really good SN curves because there's so many different factors. There's stress concentration factors, nonlinearity, there can be temperature, humidity, salt fog. There's concerns about whether the stress is one-sided, either in the compression or tensile polarities, or whether the stress field is oscillating about a zero baseline. All these things enter in to our fatigue calculations, or at least they should. but it becomes really difficult to get good SN curves that can cover these types of variables. So anyways, we just have to make some simplifying assumptions, and perhaps the best that we can ever expect for our calculations is that our cumulative fatigue damage will be to the correct order of magnitude. So please keep that in mind. Okay, now back in 1968 there were two Japanese authors, Endo and Matsuishi, and they developed the rainfall counting method by relating stress reversal cycles to streams of rainflow, rainwater flowing down a pagoda. And there's different references that you can look up. And my favorite reference is ASTM E1049-85, published in 2005. And this document is only about 5 or 6 pages long, but it gives the formulas and methodologies for actually performing this rainflow counting. So here we have a pagoda here, and there's streams of water flowing down these different roof sections. And we're going to have situations where one stream of water is going to encounter another stream of water, and there's going to be a set of rules as to how to deal with all those and how to convert our stress time history into a series of cycles with corresponding amplitudes. So here's just a sample stress time history. So stress is along the y-axis and time is along the x-axis, and you can see the various points there, and it looks like this stress time history is oscillating somewhat symmetrically about the zero baseline, but that's not necessarily a requirement for rainflow fatigue. Now, wouldn't it be nice and wouldn't it be easy if we could just say, okay, here we have one segment, then there's another segment and another segment, and just look at the stress amplitude cycles in terms of these consecutive segments. And if this was sine vibration, sure, that would work. That would work just fine. But for the case of random vibration, where we have all sorts of localized peaks and valleys, it really kind of becomes kind of nebulous as to how to go about doing that rainfall counting. So Endo and Matsuishi came up with a wonderful idea. They said, let's take this stress time history and let's rotate it 90 degrees. So now time is the vertical axis, stress is the horizontal axis, and otherwise it's the same curve, the blue curve there. Now these black curves here, these little black segments are going to represent the rainflow cycles in terms of paths. So the first path is going to be from A to B. So here we have this rainflow that's coming down, and as it falls down beneath the first roof section there, it encounters another stream of water that started from a higher absolute value. Or you could say it started at an earlier time. Well, I'm doing a little hand waving when I use the word time there, but you get the idea that this cycle, this path from C to D is taking priority, and the A to B is going to stop when it encounters the C to D cycle. So the path from A to B gets counted as a half cycle, and it has a stress range of 3. Okay, the next one is going to be B to C. So here we have B to C going down, and then gradually it's going to encounter a rainflow cycle that happened starting at a higher absolute magnitude, or you could say it started at an earlier time. So the D to E to G cycle is taking priority over the B to C cycle. So B to C stops. It gets counted as a half cycle with a stress range of 4 stress units. Then we have C to D. So this rainflow cycle is starting and continuing downward, reaches the edge of the roof, and then just falls to the ground. So it never encounters any other rainflow. C to D is also counted as a half cycle with stress range of 8. Then we have D to E to G, which we've already mentioned. And just for simplicity, we're just going to call it D to G. And then it falls to the ground. And D to G is also a half cycle, and it has a range of 9 stress units. Now the E to F cycle is interesting, and it's going to be the only path that we're going to count as a full cycle, and here's why. So E to F is starting here, continuing down, drips off the edge of the roof, and then it encounters this previously established rainflow cycle. So in that sense, you'd think that E to F is just going to be a half cycle. But what happens is, let's look at D to E to G. So from F to G, well, there is no rainflow cycle that goes all the way from F to G. So this rainflow cycle is coming down and it says, oops, I got to stop and I have to yield to this rainflow that started at an earlier time, or you might say from a higher stress magnitude point. So it turns out this E to F actually gets counted as a full cycle. And it has a stress range of 4 stress units. Then we have G to H as a half cycle and H to I as a half cycle. So this is the rainflow methodology that Endo and Matsuishi came up with. And this is just fantastic. This is brilliant work. And I just give a lot of credit to these two authors for what they came up with. Now, this is conceptually very simple. And it makes sense. And it's just a wonderful tool. Now, if you want to sit down and write a software program to do this and to follow all the rules in ASTM, well, you can kind of sort of come up with a software program in just a day or so of effort. But to tweak that so you make it completely accurate can that will take you off and on a full year. And I know that by experience. Because the rules get really intricate, and we'll talk more about the intricacies of the rules later. So conceptually very simple, but the rules laid out in that ASTM spec are very complicated. More about that later. Now, it becomes kind of a common practice, especially NASA, to say, okay, we have this all these cycles here with their various stress ranges. Well, let's sort of just group these into bins. So let's look at these stress ranges and let's come up with bins for the stress ranges, and we'll kind of sort the data that way. So this is a typical NASA type format. And let me just mention here that when we're talking about range is the peak minus valley. And amplitude is so in parentheses we have peak minus valley, then divided by 2. And you always kind of be a little careful and double check if you're looking at a paper or somebody's data, just to make sure everyone has the same conventions. But anyways, what the NASA format would be is, okay, let's come up with ranges, and these might be like 10% or whatever type ranges, and then as we get closer to the bottom, we might tighten up the ranges, whatever, and then let's count how many total cycles are falling within each bin. And there's different parameters: average amplitude, max amplitude, all these different parameters. And then presumably someone would take this and maybe feed the data into a minors type calculation. Well, it has been traditional, and Steinberg does this, for example, and as have many other authors, to sort of take our data and group it into different sigma levels, for example, and then to feed the data into a minor's cumulative fatigue type calculation. But my approach is different. I say, okay, I'll make this table just to humor the people who need to be humored in that regard. But why even bother to bin our data? Right here we have the cycles and stress ranges, and we can convert stress range to amplitude just by dividing by 2. We could just feed this data directly into our minors rule summation. Why even bother with binning? Because once we bin our data, we actually introduce some inaccuracies, because how are we going to represent the amplitudes in that bin? Are we just going to take the mean value within that bin or the max value? Well, either way, there's going to be some error introduced. So I'm just not a big fan of binning. I'll do it, but I say, here, this is all we need. It's this table. Okay, so let's talk more about the rainflow cycle counting and its uses. So rainflow I think I already mentioned this. It can be performed on sign, random, sign on random, transient, steady state, stationary, non-stationary. So just bring your own signal oscillating signal whatsoever you might have, and we can do a rainflow analysis. And one of the purposes for rainflow cycle counting is to feed that data into the miner's rule and to evaluate the potential for a failure mode using miner's rule in conjunction with the SN curve for that material. Then we can here's another use altogether that's also a powerful tool. We can compare the relative damage potential of two different vibration environments for a given component. And to do this, we don't need to know what the SN curve is, except for we do need to know what that fatigue exponent is going to be. So for example, let's say you have an avionics box and it's been qualified to one type of vibration environment, and then somewhere mid-program the requirement is changed and you have an altogether different requirement. Well, it takes a lot of time and money to qualify an avionics box, so is it possible to show that the box is good to go for the second environment based on the fact that it has successfully passed the first environment? Well, one way to compare those two environments and to gather data for making that decision is to look at the relative damage potential. And we're actually going to be covering that, let's say in a future webinar, in an upcoming webinar. We can also use the rainflow cycle counting method to derive the maximum predicted environment, or MPE levels, for non-stationary vibration inputs. Furthermore, we can, we can even let's say we have a sign on random type of specification. And this might be for, say, a helicopter, for example, or whatever you might have. But to simplify that type of specification, that test, we might want to convert that just to an equivalent PSD. So how can we come up with a PSD that covers a sign on random environment? Well, there's actually a method to do that using rainflow fatigue, and we will cover that in a future webinar. We can also derive equivalent time scaling techniques so that a component can be tested at a higher level for a shorter duration. So let's say, for example, we have a avionics box and it's going to go on a jet aircraft, and it has to be good to go for, let me just pick a number, 4,000 hours. So do we really want to put that avionics box on a shaker table and test it for 4,000 hours? No, that would be far too expensive, far too time consuming. So instead what we're going to say is, okay, we only want to test that box for 8 hours on a shaker table. So in order to justify that, we're going to test at a higher level than would be used for the 4,000 hour test. Now, does that mean we increase that level by 6 dB or 12 dB? Well, we can use rainflow fatigue to determine which way we should go, how much additional amplitude margin we need for our shorter time duration. And we'll cover that in a future webinar as well. We're in the midst of a series of fatigue webinars here. We talked about electronic component fatigue last week. Today we're talking about our rainflow cycle counting, and we probably have 4 or 5 or 6 other fatigue webinars yet to go. Okay, now rainflow cycle counting is performed on stress time histories for cases where miner's rule is used with a traditional SN curve. So this would be the case where we're trying to determine whether a hard failure is going to occur, or how much life we have, or how much margin, or whatever. But the same rainflow technique can also be used on response acceleration, relative displacement, or some other metric for comparing two environments. So as I mentioned, for the case we have the avionics box, already been qualified to one vibration test. Now it has to go undergo another test in order to weigh the two environments and to see if we can skip the second environment. We could simply do the relative damage rainflow calculation on the acceleration. So we don't need to go and actually calculate the stress, although we could. Now, if we're going to do some type of Steinberg's electronic fatigue calculations, then relative displacement would be our fatigue metric of interest. And we covered that, we started that last week, and in the next week or two, or three, we're going to revisit that in more detail. So here's our mascot for this course. It's the Springmass system. So we have mass M, spring stiffness K, dashpot C, base acceleration Y double dot, and response acceleration X double dot. So this is our system here. Now, the metric of interest as we're doing these types of calculation is going to be the response acceleration or the relative displacement. It's not going to be the base input. So let's say we're doing a test or we're gathering field data or flight accelerometer data, and we had an accelerometer mounted on this mass. Well, that would be great, because then we could take that data and say this is the response of our system, and we could feed that into our fatigue calculation. Or if we had an accelerometer on the mass and an accelerometer on the base, then we could, through some intermediate and post-processing, we could determine the relative displacement. And that relative displacement could also be fed into our rainflow cycle counting. But here's the case where we have inadequate information. Let's say the accelerometer is we only have one accelerometer. It's mounted on the base. Well, in that case, we don't have all the information we need, because the rainfall fatigue needs to be done on the response. So if that were the case, then we would have to do a base input analysis using some assumed properties to determine what our response acceleration would be. Okay, so I think I covered that already. Now we're going to do an example here, and this example comes from Steinberg. So it's just a simplified example, and what I've done is I've taken Steinberg's example and I've kind of innovated upon it and changed some of the numbers, but essentially it comes from Steinberg. But we're going to do a few enhancements to this example. So here we have a bracket. It's sort of a cantilever style bracket with fixed free boundary conditions, and it's going to be made from aluminum, and you can see the various dimensions called out. And here we have a solder terminal, and the solder terminal is going to represent a stress concentration factor because there's a hole for that terminal. Then there's a power supply. It's going to be modeled just as a point mass. It's close to the end of the beam, but not quite. And what we're going to do is we're going to subject this to a base excitation, and we're going to determine what the resulting stress is in the vicinity of that solder terminal to determine what kind of life that we have, or whether or not failure is going to occur. So here you see the various properties. This power supply mass is going to be 0.44 pounds mass. That's LBM. And you can see the other properties here. The viscous damping ratio will be 5%, and that's equivalent to an amplification factor of Q is equal to 10. And what we're going to do is we're going to do a very simplified approach following Steinberg with some enhancements, and we're going to model this as a single degree of freedom system. So we're actually going to use the Rayleigh method to determine what the natural frequency is. And then when it comes time to do stress analysis, we're going to just do a very simplified equivalent static load analysis. And every time I hear equivalent static load for an acceleration environment, I really cringe at that. And it just sort of drives me crazy that people do that. But here I am. I'm going to do it as well, because it's such an oxymoron to have an equivalent to static acceleration load. But so be it. This will kind of work just sort of as a first cut at this problem. The more proper way to do this would be a strength of materials, material mechanics approach, where we look at the strain distribution in that bracket. But we're actually going to save that example for another webinar. So today we're just doing the simplified approach, and that's okay. So we actually have a MATLAB script to calculate the natural frequency of the cantilever beam with the point mass. So let's go to vibration data. And this week we're up to version 6.5. And we're going to input we're not going to input anything yet. Rather, we're going to go to the structural dynamics option over here. Then we go to beam bending. And this is new for this week. We have a menu here where we can go to our traditional general boundary condition beam bending. And I've added another case here, special case, a cantilever beam with a point mass. And the point mass can actually be anywhere along the length of the beam. So let's see if I can remember my numbers here. So our beam length is going to be 6 inches. The thickness is going to be 0.25 inches. The width 2 inches. It's going to be aluminum, so the properties are already given there. Our point mass is 0.44 pounds. Oops, let's see if I can type correctly. And then it's going to be 5.5 inches from the fixed end. So it's going to be close to the free end of the beam, but just inside by ½ inch. So let's go ahead and calculate. So our natural frequency via this Rayleigh calculation is 94.75 hertz. So that's the spring mass frequency there. And actually I was going to try and copy and paste it, and that didn't quite work out, but here's the same frequency in the command window. Okay, so what are we going to do next? So the next thing we're going to do is, okay, so here's our spring mass system representing the bracket with its power supply. And again, we're going to assume Q is equal to 10 and with base excitation. So let's go to our library function and let's pick out a base excitation. So let's see, let's go to import data to MATLAB. And this week we have a new specification. It's actually one we've taken a look at before, but this is the first time it's in our library function. And it's Mill Standard 1540B ATP PSD specification. So let's read that. Okay, so its units are frequency in hertz and g² per hertz. So that's now loaded in, and you can see that in the workspace. Of course, if you wanted to, you could just enter in this manually as well, this PSD. So there's the 2 columns of numbers, the breakpoints there. Okay, and again, the first column is frequency in hertz, and the second is g² per hertz. And it looks like they're all zeros, but that's just MATLAB's quirky way of taking that scale factor. In fact, if we want to see those numbers, the g² per hertz numbers, those are the real numbers. Okay, let's go back to vibration data. And we're going to synthesize a time history to meet that power spectral density. Now, this is a review here, so we have time history synthesis from white noise. We've done this before. And we already have, in fact, it just pops up here. Since I previously ran this before I started this webinar recording, the name and the duration are already entered in there for us. That's convenient. So let's view our processing options. And we're going to go with the option that is about, let's see, let's do choice 10 here. We have plenty of statistical degrees of freedom, and our delta F is going to be about 2.8 hertz. So let's calculate. Okay. So here's the result of our synthesis. We have a power spectral density and the g² per hertz versus frequency in hertz. And that's in actuality GRMS² per hertz. The red line is the nominal value. The blue line is the PSD of our time history synthesis, and it's well within the plus and minus 1.5 dB tolerance bands. Here's the histogram of the acceleration time history, counts versus acceleration g. It has the Gaussian distribution. Then the displacement time history, the acceleration time history. So here's our acceleration time history. And if we zoom in, we can find out that, yes, in fact, it is a random vibration signal. It's not white noise, but rather it's a time history which matches a shaped power spectral density, which is a broadband PSD. So we're going to save this time history. I'm going to save it as synth, S-Y-N-T-H. Okay, now we're going to calculate a single degree of freedom response to that base input, which will be the response of our Springmass system. And I'm trying to make this software a little more user-friendly, so I've added a button here so we can go directly to our single degree of freedom response function. And aside from the short navigational cut, this is something we've run before. So let's put in our, nope, natural frequency goes down here. It's already entered in. Q is equal to 10, and it's synth, so we don't put in a number, rather we put in the label of our array. And that's a synthesized time history with units of time in seconds and acceleration in g. Let's calculate our response here. So we have our relative displacement response, our acceleration response, and our base input acceleration. Now the base input acceleration is a synthesized acceleration, so we've seen that before. And what about our acceleration response? Let's go ahead and zoom in on this and see what happens. So I'm going to do some successive zooming in. And you can see the frequency content is fairly sinusoidal. So if we took the number of peaks over a given duration, we would find out that that comes out to be about 95 hertz. But the amplitude itself is varying in a random manner. So what we have here is we have a narrowband random response. That's what's going on. We've talked about that before. So let's save this. I'm just going to call it Excel_RESP. That is our response. Okay, you can see the various statistics here. Now here's something that has always concerned me, and we've talked about this before, is that if we take the ratio of the peak absolute value to the RMS, that gives us our crest factor. And you could think about RMS being equivalent to the 1 sigma value, assuming a zero mean. So in many cases, when people are doing these types of analyses for random vibration, they assume that 3 sigma is the worst case. Well, for our case, we would say we have a 4.61 sigma peak. So if we are to just stop at 3 sigma, we are going to underestimate the fatigue damage and the stress levels for this component. So just keep that in mind. Okay, we've got to go back to the slides here briefly. So here was our base input power spectral density from that mill standard. And we read that in. It was a library function. We did the time history synthesis. Came up with a synthesized base input. Now this is the slide version, and it's not necessarily the same one I just generated in our webinar class here. And that just has to do with the random number seeds and that sort of thing. But the key statistical parameters would all be similar. And we verified that the synthesis time history gave us a PSD that complied with the specification. Then we took a look at the response. Okay. Now, at this point, because we're going to try and look at the possibility of an absolute ultimate stress failure, we're going to have to convert this acceleration into stress. And again, the more proper way to do this, or the proper way, is to do a strength of materials type calculation and look at the strain field along the beam. But we're going to just do an oversimplification here, and we're going to say, okay, we can do an equivalent static loads analysis, and we're going to take that point mass times its acceleration. Actually, it's going to be an equivalent mass representing both the beam mass and the point mass. And we're going to take that equivalent mass, multiply it by acceleration, and multiply it by length, and that is going to give us our reaction moment. And there'll also be a reaction shear force as well. Then once we've done that, we can determine what the bending moment is along any length of the beam. And that's just using some basic statics type approaches. So the effective mass from some previous textbook type derivations, and somewhere on my blog I must have a paper on this. In fact, I know I do. For this case, our approximate effective mass is going to be 0.2235 times the mass per length times the length of the beam plus our point mass. So for our case, our effective mass is going to be 0.0013 pounds force second square per inch. So that's our effective mass, and then again we're going to multiply that by our acceleration, which is going to be our narrowband random time history, times the length, and this length in this case is going to be the length from the effective mass. We'll call it the effective mass CG to the solder terminal. That's how that calculation works out. And the bending stress is then going to be equal to K, the stress concentration factor, times m hat, that's the effective mass time. It's actually the effective. Excuse me. Okay, I started to say m hat was the effective mass. That's not true. M hat is the resulting moment from the effective mass times acceleration times its length. Then we're going to multiply by c, where c is the distance from the neutral axis to the outer fiber of the beam. Then we're going to divide by the area moment of inertia. And for our case, for the solder lug or solder terminal mounting hole, we're going to assume that the stress concentration factor is equal to 3. So imagine that now that we kind of do a little bit of rearranging and substitutions. So in our parentheses here, we have the stress concentration factor times effective mass times the length times the distance from the neutral axis divided by I, area moment of inertia, and let's call this a coefficient. And then that will be multiplied by our acceleration time history in order to give us our bending stress time history at that solder lug mounting hole. So this just kind of shows you the calculations. It's actually a bit of a nuisance here to go through and get all the units correct and do the calculations. But anyways, after we do this kind of some busy work here, we come up with a scale factor that's going to be approximately 0.34 KSI per G. So if we apply this scale factor to our acceleration, then we're going to get our bending stress at the solder terminal hole within the scope of our simplified assumptions. So let's see how we can do this. So we have 0.34. Let's keep that in mind. So let's go to vibration data, and let's go to signal editing utilities. Let's click on that. And we're going to do trend removal and amplitude scaling. And let's see, our file here for our response acceleration is accel_RESP. So we have acceleration G and stress in KSI. And we're not going to do any trend removal because the signal acceleration response signal already is oscillating about the zero baseline. No need to do trend removal. But we will multiply by a scale factor, and that scale factor is going to be 0.34. And that will convert acceleration in G to stress in KSI. with the built-in stress concentration factor. So our input time history is acceleration versus time, and this input time history is actually the response of our mass, but it's the input to our scaling calculation. Then our output stress time history. So this is at the top, at the solder terminal hole. Already with it, the stress concentration factor is already built in. And this, because it's a simple scale factor, it's going to have the same crest factor as did the response acceleration, and it's also going to be a narrowband random process. That should be intuitively clear. And it's going to have a frequency if we zoom in enough times. So we could do the little exercise where we count the peaks and divide by the corresponding duration, and that should come out to be about 95 hertz. And if you want to do that, that would be an excellent homework exercise. So that's our output stress time history. It's the bending stress. And we're gonna save this now. Let's call it bending underscore stress. That's our output stress time history. So bending stress, save. Okay. So this slide here just shows you what we did. This is a reminder for when you go through and do this as a homework exercise. And then here was the output stress time history for the PowerPoint slide version. Okay, next we're to the point we can finally do our rainflow fatigue. That's what we've been waiting to do all class long here. So we have a time history, it's going to be stress, and we're going to do a rainflow cycle count. A lot of things going on with this dialogue here. We're going to have to carefully go over each thing. But to start with, before I forget, I want to enter in our stress time history. So that's an array. It's in our MATLAB workspace, so it's preloaded into MATLAB. And it's going to be stress in KSI. So this is vibration data underscore rainflow.m. It's rainflow cycle counting per ASTM E1049-85 2005 with credit to Endo and Matsuishi. The input array must have 2 columns, time in seconds and amplitude. Now just for convenience, since we've been working with time histories with seconds, I have that as times in seconds. But in all actuality, this time in seconds, this can be any time unit whatsoever. The rainflow algorithm doesn't care what the time unit is. It only is concerned with those sequence of peaks and how they sort of relate one to another. Now the amplitude format, and I just want to clarify this and be very careful here. This is peak minus valley divided by 2. So that's the rainfall cycle that we're going to do. There's an option for displaying a table and figure, and I'm just going to say yes and yes, although we're not going to pay much attention to either. Okay, now here's something that's going to take a little bit of time to explain. When we're doing this rainflow cycle counting, the way the algorithm is set up is that we have this array of amplitudes. And at certain points, we have to remove intermediate points from that array. And that's conceptually simple, but in terms of the internal software, that's kind of a tricky thing. Of course, MATLAB can do that. That's why we have a MATLAB direct method here. But MATLAB's method is time-consuming. So it can take minutes, hours, days, or whatever, depending on the length of the input stress time history, as well as its characteristics in terms of its spectral distribution. So it turns out that C++ can do that operation a whole lot quicker. C++ has a wonderful means for removing intermediate points out of a one-dimensional array. So C++ is much faster, and as you might well imagine, I have a C++ rainflow program, And I think I posted the source code for that on my blog if you're interested. But a lot of students nowadays coming out of college, they hardly know what a DOS prompt is. They hardly know how to run something in command line window like us old timers do that learn the old school methods. So there is a way we can use MATLAB as a wrapper to call up a C++ program, and that's our MATLAB MEX option. Now to do MATLAB MEX, we might reduce the calculation times compared with direct by maybe 1/20th of the time, or who knows what it might be, but it is a significant time saver to go with MATLAB MEX. So in order to do MATLAB MEX, you do need to have a C++ compiler installed on your PC. And these C++ compilers can be downloaded freely from different websites. The one I use is called CodeBlocks, but there's MinGW, there's Microsoft. I mean, there's all sorts of different compilers you can download. And if you need help with that or any hints or suggestions, please send me an email, or you can talk to the. Hopefully, there's a computer network person that you can go to in your company, or software guru that can help you with that. Now, once you install your C++ compiler on your machine and you're in MATLAB, you have to do a one-time thing where we go to the prompt and type in MEX _setup. And this will allow MATLAB to get interfaced with the C++ compiler. So this would be just a one-time setup thing. Then also as a one-time thing, you would need to go MEX Rainflow _mex.cpp, and that will actually compile the Rainflow _mex C++ program. So actually everything, these two steps at the command prompts are both just one-time deals. Once you've done that and completed those two steps successfully, then you're good to go for a MATLAB MEX calculation. So let's go ahead and do our MATLAB MEX calculation. For our rainflow fatigue, we're using both MATLAB and C++, where MATLAB is going to be the overlying wrapper. Calculation is very quick. So the first thing we see here is our bin table. Now, bin tables don't excite me very much, so I'm just going to, this will be a little anticlimactic. I'm just going to click out of this and say, okay, been there, done that. And here is a table showing the cycle counts with different ranges. And, okay, been there, done that, not interested. Here's our stress time history. We've seen this before. So at this point you're saying, well, that sure was anticlimactic. We just did our first rainfall calculation, and then you just, you've dismissed all those plots and tables there. What's going on? Well, I'll show you what's going on. Let's go ahead and save our rainfall cycle output. We're going to save this as amp_cyc, and this will be a resulting table. It's going to have two columns, amplitude in the first column and number of cycles in the second column. And just to show you what this looks like, I'll just do about 10 rows here. Let's see if I can do this correctly. So in the first column here we have the stress amplitudes, and in the second column here we have the number of cycles. And the number of cycles will either be a half or 1. So again, my point is, why would we ever need to bin this data? We have data here that we can directly feed into our miners calculation. Now these stress values look very low, but that's just because we're at the beginning of the signal. So what if I go out further to where the real action is happening? Let's see if I can do this correct. So once we get further into the signal, we get our higher stress levels, and these are in units of KSI. Okay, so you're still thinking, well, okay, that's, I got this table of numbers, so what do I do with that? Okay, well, before we go further, we have to come to grips with these pesky SN curves. And I say pesky because it's just you can beat your head against the wall trying to look up references and finding a good set of SN data for your particular material. And here's one that I've come up with for aluminum, 6061 T6. And let me emphasize, this is for reference only. Don't quote me on this. Do your own due diligence. Come up with your own stress cycle curve. KT here means that this curve is going to be a stress concentration factor of 1. We're going to account for our stress concentration factor of 3 separately. I'll explain that. But sometimes you'll find in references that there are different SN curves for different stress concentration factors, and you'll see references to notched and unnotched samples, for example. Stress ratio equals -1. This means that we have a symmetric stress field about the zero baseline. When I say stress field, I mean time history, about the zero baseline. But sometimes as you consult with the literature, you'll see SN curves where it's all one-sided on compression or all one-sided on tension or any permutation in between. Another concern with these curves is that a lot of these curves you'll see are just defined in maybe a dozen or so points, and so we kind of have to make our own continuous curves to connect up with those points, and it's very common that these curves actually stop somewhere above 1,000 cycles, and so low frequency SN curve data is very hard to come by. We kind of just throw up our hands and assume that this is going to converge to the ultimate stress limit. And the reason there's a slope change here has to do with ductility and strain hardening and other things of that nature. So this is max stress along the y-axis, and this is amplitude stress. Now, here's another thing that you have to be careful of. As you go through the literature, and maybe like there's Mill Handbook 5J or whatever, you'll see SN curves, and it will be ambiguous as to whether it's a zero to peak or a peak to peak. In other words, is it amplitude or range? And that's just kind of a concern I have about how SN curves are presented to us in the references. Okay, I think I've kind of covered this already. So for the case where we have above, say, 1,538 cycles, the maximum allowable stress is given by this curve, and I've simplified it into a straight line segment in log-log format, even though in actuality you can see there's some curvature there. So, back to the earlier statement I made, this is all ballpark calculation. And at some point we have to say we cannot agonize any further. Our report is due by 5 p.m. We got to get it done, so we just have to make a simplified assumption. Now into the miner's cumulative fatigue. So let n be the number of stress cycles accumulated during the vibration test at a given stress level represented by the index I. And that when I say that, that's going to be lowercase n. And uppercase n is our not to exceed number of cycles, which would otherwise produce a fatigue failure at the stress limit for the corresponding stress value. So this is the classic miner's cumulative fatigue index R. So we do this summation. And the people that like to arrange the rainflow cycles into say 3 bins or a dozen bins, whatever, are very proud of themselves. They can just pat themselves on the back because they say, oh, all I have to do is throw in a couple of ratios into this formula, and then there we have our cumulative damage index R. And I say, well, okay, but in order to bin the data, you've made some assumptions that have kind of potentially introduced some inaccuracy. And why not take all 2,000 or 3,000 or however many stress reversal cycles we have and feed that into the summation, the software doesn't care. I mean, our software nowadays is so quick that we don't need to make this a hand calculation. The software can take care of this for us. We don't even need to do our binning. But anyways, in theory, according to this miner's theory, the part should fail when the R value reaches a value of 1. But for conservatism, for example, Steinberg says that aerospace electronic structures should have a more conservative limit of 0.7. And if you want to be even more conservative yet, I'm sure you could find or a lower not to exceed R, or just make one up yourself. Now, actually, as it turns out, the people that do fatigue analysis like to simplify this a bit further. And they say, well, we can take that SN curve with its 2 segments, and we can just simplify this into a 1-segment SN curve. And this is going to be okay as long as the stress is going to be below the ultimate limit with some margin to spare. So let's just go back to our aluminum curve here. We're going to assume that our stresses are well below the ultimate stress limit. And we're just going to take this and simplify this as a single curve here. And the single curve here is going to have a point where it intercepts the cycle, where the cycle would be equal to 1/2. And that point where it intercepts where the cycle would be equal to 1/2, that is going to be called the fatigue strength coefficient. We'll talk more about that here shortly. So here's our very simplified method here. And this will allow us to do an equivalent miner's calculation where we directly calculate the fatigue based on the stress cycles. So let's directly calculate the fatigue based on the stress amplitudes, I should say, cycle by cycle. And we have to take this stress and raise it to the exponent b. And then we can divide by this fatigue strength coefficient, which I mentioned earlier. And it's the stress limit for 1/2 cycle for the 1-segment SN curve. And in actuality, it's that stress limit raised to the exponent of b. And as I sit here doing this presentation, the more I think about this is that even though this is a neat and tidy formula in the literature, we really ought to be using the full SN curve, including our assumptions for how this curve kind of has the little roll-off effects and does not exceed the ultimate stress limit. But more about that later on in future webinars. Just for today, we're going to do this simplified calculation. So let's go, and we're going to do the second part of our fatigue calculation, or I should say the next part. So we have amp underscore CYC here, which we've saved. Okay. Let's go to our miner's cumulative fatigue, which is valid for stress time histories. And this script calculates the Palgram miner cumulative fatigue damage. So let's type in our stress array there. It is units of KSI. It is duration of 180 seconds. And aluminum 6061 T6, we see the exponent there. And we have the fatigue strength coefficient A, and it's KS in units of KSI raised to the power of 9.25. Now we already have our stress concentration factor applied. So instead of typing in 3 here, which is the stress concentration factor, we're going to type in 1 because we've already applied that in our stress time history. Now our cumulative damage is not going to depend on duration, but the cumulative damage rate will depend on duration. So let's see what our cumulative damage is. And that comes out to 2.229 e to the minus 8. And that is so well below 1 that we can say we probably never did we probably did not even need to do this calculation in the first place because uh, our part is going to last for a very long time at that level. But sometimes what I like to do is once I get these numbers is I like to say, well, okay, what if we had raised that level by 3 dB or 6 dB? So let's go to this table here, and we see, okay, for our input level of 6.1, and let me start off with the table header here. This is our single degree of freedom system, our solder terminal location, and we have the fatigue damage results for various input levels, 180-second duration, crest factor equal to 4.53. Well, that was for the slide version. For our in-class version, we had a higher crest factor. And then for, let's see, for our slide version here, let me go back and check our, let me just go back here to our, okay, it turns out our in-class exercise yielded a cumulative damage, which is very close to the slide version. So that gives us some extra confidence. So then I went through and said, what if we raised our input level by 3 dB increments? So here you see the GRMS value increasing. Here you see the margin, the 3 dB margin, then 6 dB, and so on. And the stress values are going to go up by the corresponding margins. So we don't need to go through and do all those calculations again. We can just simply do some scaling here. Everything is going to be assumed to be linear. So you can see the stress values going up. Now for a 3 dB margin, being that these are amplitudes to the first power, the increase is a scale factor by the square root of 2. So you can see the input overall levels are going up by a scale factor, a square root of 2, as are the response stress values, also likewise going up by a square root of 2. So you can see that happening there. Now the R value, the cumulative damage, look at what happens there. The R value is definitely going up by higher than square root of 2. And let me just go to an Excel spreadsheet here. If we take the square root of 2 and we raise that to 9.25 as the exponent, that's about 24.7. Let's just call it 25. In each case, our R value is going up by a factor of 25, corresponding to 3 dB increments. And finally, when we get to a 15 dB margin, we can see that the damage is approaching 1 here. It says 0.219. So it looks like that our part would not be able to survive much longer than 180 seconds with a input margin of 15 dB. So that kind of just teaches you some more things about fatigue. Let's go back to our MATLAB command window here. So here's our cumulative damage. Again, cumulative damage in terms of minors does not depend on duration, but our damage rate does. So here's our damage rate per seconds. So if we take that damage rate per seconds, we say, okay, at what point will our damage rate be equal to 0.7? I should say, at what duration will our damage be equal to 0.7? That's the number of seconds. That's a huge number. So then we can sort of play around and do a little game here and say, okay, there are 3,600 seconds in an hour. So how many hours? How many hours can our part withstand at that input level? Quite a few. Oh, oops. Okay, keep me honest here. That's the number of hours. That's still a lot of hours. How many days? How many days? Quite a few. Quite a few days there. How many hours? Excuse me, how many years? I get a little tongue-tied here. You're just going to have to put up with that. Okay, 179 days, if I've done that right. Let me see. So we converted, we calculated the number of seconds based on the damage rate, calculated the number of hours, the number of days, number of years. Okay, I see what's happening. 180 years. So in other words, at this nominal input level, 6.1 GRMS, uh, this part can outlast our lifetimes. So it probably was not necessary to do the fatigue calculation, but what if we had a higher level? Particularly, say for qualification levels, we would typically add 6 dB, sometimes 3 dB, but sometimes 6 dB to go from an acceptance vibration level to qualification level. So in that case, the fatigue damage is much higher, and the part would have a shorter duration, a shorter lifetime at that level, but still plenty long enough to pass the corresponding shaker table test. So after all was said and done, our example was kind of anticlimactic, but you get the idea of how to do fatigue calculations. And this is just sort of, as I mentioned, an introduction, and we certainly need to cover more aspects of rainflow fatigue calculations. We're going to, in our next, in some of our upcoming units, instead of just doing these simplified Springmass system simplifications, we are going to look at these beams and plates. We are going to look at beams and plates using continuous models, so we can account for the stress and strain fields, which will make for a better calculation. But that's all for now. Please repeat this as a homework exercise, and we've certainly got more to do. So look forward to seeing you next week, and have a good day.